Hello, welcome back to this lesson in algebra where we're going to learn how to solve polynomial inequalities. So in the last 4 lessons, we've actually conquered the idea of solving polynomial equations. So you have a polynomial like x squared plus 2x plus 3 equals 0. That's solving a polynomial equation because you have an equal sign, right? Now we're going to circle back and go revisit the concept of an inequality. Now we've done lots of inequalities in this class. Open inequalities, closed inequalities, graphing inequalities, absolute value inequalities. We did all that stuff a long time ago. But those inequalities, all of the ones that we've done up until now, have just been with x raised to the first power. Just like we learn lines before we learn parabolas and other quadratic stuff, polynomials, and lines are just single power of x, mx plus b. So we learn how to do lines, then we learn how to do more complicated equations, and we've learned how to do the basic inequalities. Now we're going to learn how to solve inequalities that have a polynomial involved. And as you might guess, you're going to have to factor those polynomials to get anywhere in the solution. So before we get started, let me just draw a parallel and show you how this stuff comes from what we have already learned. So I want you to recall the idea of inequalities with one variable in the way that we've done it before. So we might have in the past had something like x plus 2 greater than 3. That is an inequality that we've learned how to solve and graph it. And how did we do it? We take what's over here, we isolate the variable x, we pretend there's an equal sign, we subtract 2, So what we end up with over here, I'll just write it over here to save space, x is greater than 3 minus 2, so x is greater than 1. So what this means is that since this is not an equation with just one solution, this is an inequality with this has to be greater than 3. That means that there's a whole bunch of values of x that are going to work for that inequality. So in this case, we're saying x is everything bigger than 1. So if we have 2 in there, that's 4, that's bigger than 3. If we put 3 in there, that's bigger because it's 5, and so on and so on. As we increase x anything beyond the number 1, we have satisfied the inequality. And we know how to graph those inequalities. We've done all of that stuff before. Draw your number line, put an open circle at the number 1, open because there's no equal sign there, and then shade to the right of the number 1. We've done all that before. If you've never done that, please go back and do that now and meet me back here. So I'm showing you memory lane here, just a trip down memory lane, because I want to draw the parallel to what we're doing now. So this was an inequality like we've done before. This is just a linear inequality because it's just an x to the first power kind of deal. Now, what if I give you the problem something like this? What if I give you x minus 2 times x minus 5, and I say that that's less than 0? What kind of inequality is this? Is this going to be a linear inequality like this, or is it going to be something else? And the answer is going to be, this is called a polynomial inequality. Why? Because if I were to multiply all this out, see in the beginning I give you problems that are already factored to make it easy, but if I were to multiply all this out, I'd have x squared, I'd have an inside term, I'd have an outside term, and then I would have positive 10. So that would be this whole thing over here less than 0. So you can see when you multiply it out, it's not a line, it's a quadratic, it's a parabola. Remember, anything with an x squared as a function looks like a parabola, so it's not a line at all. But the same sort of thing applies. We're still trying to just figure out values of x that make this inequality true. Just like we were just trying to figure out values of x here that make this expression larger than 3, here we're trying to figure out any and all values of x to make the product of these two things less than 0. So let me ask you a question. If this were not an inequality, if it were an equal sign, how would we solve it? Well, you've already learned that if it's an equal sign, we just set this equal to 0, which means it could multiply and make everything 0. And also separately, we could independently set this equal to 0, doing the same thing. We have 2 constraints to make it equal to 0. But now we don't care about it being equal to 0 at all. Notice there's no equal sign there. All we want to do is make it less than 0. We want to make it less than 0. So we have to think a little bit more carefully about that. The way you handle it is like this. First, move everything to one side. That's already done in this problem. Next, factor whatever polynomial you have. That's already in this problem done because it's the first one we're doing. Once you get it into this form, we need to think, how can we make this product less than 0? Well, there's only 2 ways that you can do that. If we're going to make it less than 0, that means we want the product of these to be negative. That's what less than 0 means, right? So there's a couple of ways we can do that. We can say this term can be, let's start out like this. This term can be negative while this term is positive, or we can make this term actually positive while making this term negative. So if for some crazy reason we knew that x minus 2 happened to be negative, while at the same time knowing that x minus 5 is positive, then if we multiply negative, this whole thing being negative times this whole thing being positive, that would give us a negative result. That's all we're trying to do. We want to make the product of those polynomials, those binomials, negative, meaning we want it to be less than 0. Alternatively, this one could be positive, this one could be negative, it'll do the exact same thing. So those are going to be our constraints that we need to solve this problem. So the way you write it down is you go and write the signs down that will make the thing less than 0, and then you have to write a couple of constraints. There's going to be a lot of little cases here. This is how I want you to write it for every one of your problems. So we first look at the top case here. So we want to say, in this case, if it's negative here, what we're going to basically say is that x minus 2 has to be less than 0, and we're going to write the word and x minus 5 greater than 0. So if we make x minus 2 negative and we make x minus 5 positive, then in that case, when they multiply, you will always get what we're trying to get over here in your problem, right? And then what I want you to do is I want you to draw like a little, almost like a vertical line. I want you to write the word or, because there's another case here. Remember, this can be the case or these can be the case. So for this other case to be true, we can have x minus 2 can be greater than 0, and I want you to write the word and, x minus 5 being less than 0. These are the only ways that this inequality can be satisfied. There are no other ways to make the product of these two terms negative. There are no other ways. Either this one has to be negative and this one has to be positive, or this one has to be positive and this has to be negative. That's why we're writing the words and to tell us, hey, these two things both have to be true, or totally separate from that, these two things both have to be true. And those are the only ways that this thing can work. Now the good news is the math is very simple for these because the little inequalities that we have are simple. So the way that we write it down is we solve this one, we move the 2 over and we say x less than 2 because we add 2 to both sides. And then we can write the word and again to remind us that both have to be true. And then x greater than 5. We just add the 5 to both sides, okay? Then we go to the other side and we do the same exact thing. We add the 2, so we say x greater than 2 and x less than 5. So all we've done, let me just double check myself, x greater than 2 and x less than 5, x less than 2 and x. So this and this, or this and this. That's how I want you to write this. All right? Now the next thing I want you to do is once you write down basically the solution, I want you to graph these things to take a look at both of them. Let's start with this one first. So we'll graph this solution. This is an and here. So if we were going to graph it, we would draw a little number line, right? The magic numbers we care about are 2 and 5. So let's go ahead and put 0 on the number line. 2 is about here. 5 is somewhere over here. Of course, you know there's 1, 2, 3, 4, 5. I'm not going to write all the tick marks. I think you guys are to the point now where we don't really need to do that. And they're open circles when I graph them because there's no equal sign underneath these guys, right? So what I'm saying is that x has to be bigger than 2 and at the same time less than 5. The only way this can happen is if the values of interest lie between these two, right there, right? So bigger than 2 and at the same time less than 5. That means it can only be this segment of values on the number line. All right, now separate from that, let's go and take a look at what this solution would be, right? So you can go ahead and put 0, the magic numbers here, you can put 2, you can put 5. Now, this one is saying that x has to be less than 2, meaning everything this direction, and at the same time, and bigger than 5. Now, your first inclination might be to shade less than 2 and bigger than 5, but the problem is there is no way that a value of x on a number line can be less than 2, but at the same exact time be bigger than 5. There is no number. Just think about it. Can you think of a number less than 2 and also and? That's why I keep telling you, write the word and also bigger than 5. It's not possible. So you write down not possible. Then we remember, the only way this can be the case is if this is true or this is true. So to find the final solution, we combine both of them. Of course, this contributes nothing because there is no solution to this. So really, this is the final solution, right? So we can draw the number line here, and we're just going to copy exactly what we have here, 0, 2, 5, and then the shaded solution area is going to be exactly what we have before. Open circle, open circle. I'll shade the line right there so you can see it between 2 and 5. And then in terms of numbers, if we have bigger than 2 and less than 5, remember back when we did absolute value, because it's a line segment, the best way to write that is x is bigger than 2 at the same time being less than 5. And you write this, or you read this from the inside out. X bigger than 2, x less than 5. So it's a segment. So this is what you would write on your test. Now, what does this solution actually mean? It means that those are the range of values of x between 2 and 5, but not including 2 and 5. So, right? So anything in that range, if you plug those values into the original inequality, it'll satisfy it. So let's just pick a number. Anything bigger than 2, less than 5. Let's pick 3. If we put 3 in here, 3 minus 2 is 1. So remember the value of 1. And then 3 minus 5 is negative 2. So 1 times negative 2 is negative 2, which is less than 0. And what you will find is that anything in this range, when you stick it in here, is going to be less than 0. Let's just test it by putting something outside the range. Let's put the number 0 in here. 0 minus 2 is negative 2. 0 minus 5, negative 5. 2 negatives multiply give you a positive, which means it doesn't work. If you pick something to the right of it, let's pick the number 6. 6 minus 2 is 3. I'm sorry, 6 minus 2 is 4. And then 6 minus 5 is 1. So 4 times 1 is 4. And that doesn't satisfy either. But any number in this range will work. So that's the general idea we're going to do. I know it's a pain and it's a little bit weird to do, but what we're going to do for all of these polynomial inequalities is we're going to figure out what signs do we need to have to make it multiply and be bigger than smaller than 0. Then we're going to take each of the cases and write them out for each of the cases. We're going to graph each of them to figure out what solutions for each side we have, and then we're going to combine them. Now in some cases you'll have a graph here and a graph here, and you'll have to merge them into the final solution, because remember, either one of these being true does make the answer correct. So you have to kind of merge them into one final solution. It's just in this case there was nothing here that worked, so it kind of dropped out. So in the next one, it'll be a little more representative of what we will see. What if we have the polynomial inequality z squared minus 4 times z greater than 0? And I want to solve that. Well, first of all, you notice that everything's on one side, but you have common terms here. So I can factor out a z. You always should try to do that. Z minus 4 greater than 0. Now what we're saying is that we want the product of these terms to be bigger than 0. So whereas over here we were trying for the product of the terms to be less than 0, that made us choose opposite signs here because that's the only way you can get negative numbers. But over here we're trying to multiply two things to give us positive numbers. There's also two ways to do that, because to get a positive number you can have positive, let's say positive 4. You can have 2 times 2 is 4, that's 2 positive numbers, or you can have negative 2 times negative 2 to also give you positive 4. So you can have 2 positives to multiply to give you a positive. You can also have 2 negatives to multiply to give you a positive. So again, the only way you can make the product of these bigger than 0 is for the first term to be positive while the second term is also positive, giving you a positive number. Also, the first term can be negative while this term is negative. Multiplying together can also give you a positive. So then we just take each case separately. In the first case, z can be bigger than 0, that's what this one is, while at the same time, we'll put the word and, z minus 4 can be bigger than 0, so they're both greater than 0. Okay, and then you can write the word or. The following cases can also be true as well. You can have z be less than 0 and z minus 4 can be less than 0. So you have both positive or both negative. That's the way you write that. And then we just cruise on through and say, all right, let's solve them. So this one's already solved, so I'll just go ahead and write the solution, z greater than 0. This one means z greater than 4. We just move the 4 to the other side. This one is already solved, z less than 0. This one, z less than 4, means we just move 4 to the other side. We're going to write the word and here. We're going to write the word and also right there. So the next step that I want you to do is I want you to graph both of them so you can visualize it easier. So I want to graph this one underneath here. The magic numbers we care about are 0 and also 4. So we'll put 0 and 4 right there. And then what we're saying here, you got to think for a second, okay? Because what this means is a number, some number, whatever it is, z we call it, has to be bigger than 0 while at the same time being bigger than 4. Think about that for a minute. How can a number be bigger than 0 and also be bigger than 4 at the same time, right? Well, that means that the number has to be bigger than 4. Take the number 5, for instance. 5 is bigger than 4. 5 is also bigger than 0. So the only way that this AND can be satisfied is if the set of numbers that satisfy this inequality, I have to put an open circle because there's no equal sign there, but they're all going to be bigger than 4, off to positive infinity. You know, 5, 6, 7, 8, 9, 10, and so on is bigger than 4 while at the same time be bigger than 0. But if I pick the number 2, for instance, that's bigger than 0, but it's not bigger than 4, so it's not part of the solution set. So you have to think a little bit when you graph it, and that's exactly why I want you to do that. Okay? So this solution here, the solution to this AND, even though we have it written as two things here, really the solution is z greater than 4. Even though up here we wrote it as two different things, really when you combine it logically, it really can only be bigger than 4 in order to make this true. Then we want to go ahead and graph this one. The magic numbers are 0 and 4 again, and we have to think again logically. We have a situation where z is less than 0, but at the same time z is less than 4. And if you think about it for a minute, the only way that you can have a number less than 0 and also less than 4 at the same time is if the numbers really are just confined to be less than 0. In other words, -1 down here is less than 0, while at the same time being less than 4. So it's all of the negative numbers here. But if I pick a number like over here, 3 is less than 4, but 3 is not less than 0. So we have to mentally combine these and figure out what's really happening. So even though the solution implies that we're going to have a lot of stuff, really the solution here is z less than 0. So we write all of our constraints down. We write the left-hand side, we write the right-hand side. We distill it all down to two things, z being bigger than 4 or z can be less than 0. So what we want to do is we have to combine both of these ideas into a final solution. So I recommend graphing it first. And this is an OR, right? So what we're saying is, let me write 0 here and 4 here. What we're saying is that z can be bigger than 4 or z can be less than 0. Bigger than 4 or less than 0. Bigger than 4 is this way, less than 0 is this way. And we don't get into problems because, you know, a minute ago I was saying, how can it be bigger than 4 and less than 0 at the same time? That's because before, when we were running into that problem over here where it was impossible, that's because it was an AND. It had to fit in there at the same time. Here, we're saying that it can be bigger than 4 or be less than 0. Or means you can have two different directions going the same way. Either set of numbers is okay. Okay? And then in order to write it down as a final solution after you get the graph on the paper, you just simply write down z less than 0 or z greater than 4, which is kind of what we already wrote down here. This is what you would circle on your test. You would graph it. So in general, OR graphs, when you have an OR, they're going to point in opposite directions going like this. And AND graphs, we're going to write as a compound inequality like this, and it'll be a segment. As far as the idea and how to read these things and OR versus AND and all that, I covered all that stuff when we talked about graphing inequalities the first time in this class. So if you need to go back and look at that, please do. That's why we cover it, because when we get to the more complicated cases, we're using those ideas, right? But the same idea holds. We look at the constraints because of this line, and then also the constraints of this line. We get it down to what these individual solutions are, then we merge them into the final solution. So let's take a look. Let's find something that doesn't work. We're saying something in the middle doesn't work. So the number 1 is not part of this. We put 1 in here. 1 squared is 1. 4 times 1 is 1. 1 minus 4, -3, is not greater than 0. But if we go over here to 5, 5 we think is a part of the solution. 5 squared is 25. 4 times 5 is 20. 25 minus 20, that's 5, bigger than 0. Correct. We go over here to -1. We think that's part of the solution. To do the next one with the signs, it can get a little tough. So to put -1 here, we think this is in the solution here. What we're saying is that -1 squared minus 4 times -1 is greater than 0. -1 squared is +1, And then this becomes positive 4, which is indeed greater than 0. So we've shown that numbers over here satisfy the solution, numbers over here satisfy the solution, but the numbers in the middle don't satisfy the solution. That's what we're trying to point out. All right? So we just have a couple more problems. I know they're not the most fun type of problems, honestly, but we need to cover them because these are the kinds of things that you'll generally trip up on your test. So I want to give you a lot of examples. So in the previous problems, I kind of gave you sort of easy to factor things, or maybe even I already gave it to you in factored form. But in the next problem, you might have something like x squared minus 5x plus 4 being less than 0. So here is a trinomial that's not factored, and we're saying it's less than 0. So step 1 is going to be to go ahead and factor this. Once it's factored, then we just solve it exactly like we've done the other problem. So we try to factor it. We're going to say it's less than 0. We have x squared, so we put x and we put x. 2 times 2 is 4, but I don't want to do 2 times 2 because I know that if I try to add 2 and 2, I'm not going to get 5. So the numbers that I think are going to work are 1 and 4 because 1 plus 4 is 5. So I think that that's probably better. And I need a plus sign here, but I have a minus sign here, so from experience I know it's going to be minus minus. You go ahead and check yourself. X times x is x squared. These multiply to give me the positive 4. This is negative x. This is negative 4x. They add together to give you the negative 5x. So what this is saying is we want this multiplication to be negative, less than 0. The only way that can happen is if this one's positive while this one's negative, or this one can be negative while that one's positive. Those are the only two ways that it can happen. In other words, this has to be an opposite sign of this one to be able to multiply to give me something less than 0. So I write both of those cases down. I say, all right, so if I'm going to go with this one, I'll say x minus 1 bigger than 0 and x minus 4 less than 0. That's writing down these two cases. Okay. Then I could say or, come down here, the bottom case, x minus 1 less than 0 and x minus 4 greater than 0. So I've covered the top case here, or the bottom case can also be true, right? So then we just solve them. And these are really simple to solve. You just move the 1 over, so you have x greater than 1 and x less than 4 by adding 4. And then over here you have x less than 1 and x greater than 4, just moving them over there. Then what we do is we graph each one of these guys and figure out what the solution, the distilled solution is on each side, or what the, what each side really yields, and then we combine them at the end. So let's try to graph this to see what kind of solution we really have. Magic numbers are 1 and 4, so here's 0, here's 1, over here is 4. So I look at this and I say, how can numbers be larger than 1 while at the same time those same numbers be less than 4? And because I don't have any equal signs, I'll use open circles for both of these, and the way you graph that is a shaded area between those guys, because these numbers are all bigger than 1 while at the same time being less than 4. All right? Now we go over to the other side, and we graph this one. Magic numbers are 1 and 4 again. Here's 1, here's 4. And I try to graph them, and I say, how can I find numbers less than 1, but at the same time, so less than 1's over here, but at the same time being bigger than 4. Now this is an and. The numbers in the solution have to satisfy both at the same time. And there is no way for a number to be smaller than 1, but at the same time be bigger than 4. It's not possible. So I just write not possible. So this side, even though we had to write it down as a logical possibility that we could have negative positive leading to this, really it doesn't actually work out at all. There are no numbers that can make x less than 1 while at the same time making x greater than 4. So really, even though we're combining them, we end up discarding what's on the right-hand side, and the real final solution of the whole thing, you just copy down what you have, 0, 1, 4, and we do a circle at 1, circle at 4, shaded region between. And then the way you write it down is you say greater than 1, less than 4. But because it's an and, the better way to write it, we write ands like this. Bigger than 1, less than 4. You read it from the inside out. X is bigger than 1. That's going this way. X is less than 4, going this way. So this is an and type of inequality. And that's what we have. So bigger than 1, less than 4, shaded between 1 and 4 with open circles. Checking myself here. So this was done exactly the way that we did the last problem. Only difference is we factored it first. Now you can see why we spent so much time on factoring, because if you don't know how to factor anything, then you can't solve any polynomial equations at all, and you also can't solve any polynomial inequalities at all. So it's very, very important. Last problem of this lesson is going to be t squared greater than or equal to 9 times t minus 2. 9 times t minus 2. All right, so what we have is we have some t's on the left and we have some t's on the right. So much like I told you with the polynomial equations that we solved, I said, hey, if I have variables on the left and variables on the right, I want you to multiply everything out, collect everything on one side, and then proceed with the solution. And that's what we have to do here as well. The t squared is totally, fine, so we'll just leave it there for now. But first, let's distribute the 9 in to give us 9t minus 18. Just distribute it into both terms. And then after that, let's go ahead and subtract the 9t and add 18. So what we'll get is t squared minus 9t plus 18 greater than or equal to 0. Notice we have an equal sign now under the inequality. So we subtract 9t, goes away here, and pops up here. We add 18 and it pops up over there. Now we can't factor anything from every term out, so the next thing we do is we try to factor it. We know that t times t is going to give us t squared, and then we have to think about what to do for the 18. Now I know that 1 times 18 is 18, but there's no way I can add those and or subtract them and get 9. I know that 9 times 2 is 18, but if I take 9 and add or subtract 2, there's no way I can get 9 out of it. But I also know that 6 times 3 is 18, and I know I can add those together to give me 9. Ignoring the negative sign here, I'm just looking at the absolute value. I have a positive 18, so I might put a plus plus there, but if I do that, there's no way I'll get a negative, so I need to put my minus minus there. And then you check yourself. T times t is t squared. This times this gives you the positive 18, negative 6t, negative 3t. Add them, you get negative 9t. So that's the answer to that. What we're saying is the product of these guys has to be bigger than or equal to 0. So for the time being, I want you to ignore the fact that it can be equal to 0, all right? And just focus on the fact that the solution needs to also be able to be bigger than 0. That means positive numbers, right? So that means this can be positive and this can be positive, or this can be negative and this can be negative. Those are the two ways to get a positive answer. Ignore for the fact now that it can also be equal to 0. So then what we do is we take the top line and we say, well, that implies that t minus 6 has to be positive and t minus 3 has to also be positive. And then you can say, or, over here we have negative, negative. So we say t minus 6 can be negative and t minus 3 can also be less than 0. So those are all of the cases that we have. All right, so then we solve everything. We solve this by saying t greater than 6 and t greater than 3. We just move the 3 over, move the 6 over. And then this one is t less than 6 and t less than 3. Again, just move the 6 over, move the 3 over. We join them with an and sign. The next step is what we want to do is we want to graph this and just see what the solutions look like so that we can merge them in the end, because either one of these being true can make the whole thing true. So we draw a number line. We say our magic numbers are at 3 and 6. So here's 0, somewhere over here is 3, somewhere over here is 6. And what we're saying is that somehow we need numbers to be bigger than 6, but at the same time being bigger than 3. So we need them to be bigger than 3, all right, but they also have to be bigger than 6. So the only way that can happen is if you have, and one thing actually I just noticed I kind of screwed up on. When I wrote these down, it should be greater than or equal to 0. So this is greater than or equal, less than or equal, less than or equal there. And then what we have here is we're going to have this, we're going to have this, we're going to have this. So basically you put a less than under, or equal to under all of the inequalities. I'm sorry about that. Then what we have next is we say, well, in order to be bigger than 3, but at the same time bigger than 6, it basically has to be larger than 6. And we use closed circles now because we have the equal signs under. So anything bigger than 6 is going to satisfy this and at the same time satisfy this. So this is possible to have. You know, in some cases that's not possible, but in this case it is. They line up where it's possible. right? And then the other thing we can do is we can graph this one. We'll put the magic number 0, 3, 6 as usual. How can we have a number less than 3, but also being less than 6? If it's less than 3, it means it needs to be over here. If it's less than 6, it's anything over here. Both of them can be true only if we put a solid circle here and shade everything left of 3. If it's left of 3, that means it's less than 3, but that by definition also means it's less than 6. So what you should do then, once you distill it all down, since we basically combine them into a graph here, really numbers bigger than or equal to 6 satisfy this graph. Numbers less than or equal to 3 satisfy this graph. So you see what we're doing. We put the constraints down, we write them down, we mentally combine these, and it turns out that only this part of the solution actually can satisfy both, so we write that down. Same thing with this. And then now for the final thing, since both of these being true can satisfy, we need to combine them together. So let's combine them first as a graph. If we were to combine these two things, how would we do it? We would say, well, here's 0, here's 3, and here's 6. This one is saying numbers bigger than 6, including a shaded region here. So we'll put this here. This can be true, or, this is an or, not an and. This one can also be true. So solid line here, or solid dot here going to the left. So numbers bigger than 6, or, meaning totally separate part of the graph, or numbers less than 3 can also be true. So you just write it down straight away. You say, write it down here, and look at this. I put X's everywhere. I'm sorry about that. This should be a T greater than 6, and this should be a T less than or equal to 3. So what you write down is T greater than equal to 6, T less than equal to 3. Put it with an or like this. Okay? Basically, when you see in your graphs segments on the number line, they're ands, and they're written as compound inequalities. When you see kind of like areas shaded on the graph in opposite directions, those are ors, because there's no way that you can have this and this. Those are ORed together. Besides, we put it as an or in there in the problem anyway because of the way it all worked out, that this constraint can be true or this set of constraints can be true. So less than 3, bigger than 6. Notice that we have solid dots, so the numbers 3 and 6 are inclusive. So for instance, if we put the number 3 into this, and we'll do it with actual pen. Let's put the number 3 in. What we're saying is 3 squared, is that greater than or equal to 9, 3 minus 2? What we'll get is 9 greater than or equal to 9 times 1, right? Which is 9. So 9 is greater than or equal to 9. Because it's exactly on the dot, it means it's actually equal, so that works out. 6 apparently also works as well. So if we put that in there, 6 squared greater than or equal to 9, and then we have 6 minus 2. So 6 times 6 is 36, greater than or equal to 9 times 4. 9 times 4 is 36, so we have an equality there. So anything bigger than those numbers in each direction will satisfy the inequality. What about some number in the middle? Like, let's pick 4, which is obviously somewhere over here. If we pick the number 4, then what we're saying is 4 squared greater than or equal to question mark 9, 4 minus 2. This will be 16 greater than or equal to question mark 9 times 2. 16 is not greater than 18, so it's false. And that makes sense because it's not in our solution set. So I'll admit, these problems are not particularly fun for me either. I don't love them, but we need to talk about them because you will be required to understand them. And it requires you to be logical. It's what I've said in algebra a lot. You know, you get to the point where the math is not so cookie cutter how you get to the answer. You have to logically think, okay, this could be true or this could be true. And then you have to go down and say, okay, well, this graph or this graph, then you have to merge them. And so I tried to give you enough examples to show you that. But all of these problems have been solving polynomial inequalities that had a square term, which means they were quadratic, just a power of 2. In the next lesson, we're going to solve some polynomial inequalities that have a higher degree, maybe a cubic. And that requires us to think a little bit harder. It's not super difficult, but we do have to think a little more carefully to get those kinds of more complicated problems solved. So make sure you understand these. Follow me to the next lesson. We'll continue solving polynomial inequalities, but in the next section of higher degree than 2.